Hi, calculus. I feel pretty guilty that I can't be with you here today, but you know what? Life happens. So, for cross sections of area A taking perpendicular to the x-axis, we're doing the drawing or the visual you saw the other day where I had those pieces of paper and it was the area under the curve, or excuse me, the volume under the curve as a sum of the area. That little drawing didn't really help, but we looked at them last week. And we figured out that the volume is the sum of all of these areas. So volume is equal to the integral from a to b of a of x dx, where of course a of x is the area of whatever cross section we're interested in. And this can be true if we're perpendicular to the y-axis as well. The only thing that's really changing is our bounds would change. I'm going to say c and d, and this would be a of y, a function of y with respect to y. So small things that we should remember: area of a square would be length times width, but length and width are the same. Area of a rectangle, length times width, but length times width are different. Area of a triangle, 1/2 base times height. And area of a circle, pi r squared. Those are probably the ones we're going to come across. Let's look at this first example. We will start by graphing these functions. F of x is line 1 minus 1/2 x, so I know it has a y-intercept at 1, a slope of negative 1/2, down 1 over 2, down 1 over 2. And my second function, y-intercept of negative 1, but I'm going up 1 over 2, up 1 over 2. And then last but not least, the line x equals 0, or our y-axis. So here is the region I am interested in. And in order to find any volume here, I need to figure out what this base is. So because we're doing cross sections that are perpendicular to the x-axis, I know that this distance right here is the base of whatever shape. In this first one, we're going to be doing squares, but in the next one, they won't be squares necessarily. But anyway, we got to find this length right here, and luckily we've been doing it all along. So if I want to find that length, I'm going to take the upper function, f of x, minus the lower function, g of x, and that would be 1 minus x over 2 minus negative 1 plus x over 2. When I simplify, I got 1 minus a negative 1, I got positive 2. I get negative 1/2 x minus 1/2 x, and then I get minus x. So this is this length right here of any of those cross-section bases. And in this case, that's the base of the square that we are interested in. So how do we set up our integral? Well, the volume is the sum of all of the areas. So the, oh no, not yellow. The integral, what's our lower bound and our upper bound? Well, we're going perpendicular to the x-axis, so we're going to go from 0 to 2, where these two functions intersect, of the area of a square. So in this case, 2 minus x, quantity squared, dx. And we can either do this using u substitution or foiling. I'm going to foil because that to me seems, I don't know, better. This is really the integral from 0 to 2 of 4 minus 4x plus x squared dx. And when I take this integral, I get 4x minus 2x squared plus 1/3 x cubed, and we're evaluating it from 0 to 2. Luckily, because each of these terms has an x, this 0 bound doesn't really matter to us very much. And so we plug in 2 in each of those places. If you want to pause the video to do it for yourself, you can do so. Otherwise, I got 8/3 as the volume with cross sections that are squares. Let's try another one. What if our cross sections are semicircles? Again, we're doing perpendicular to the x-axis. So what we've got here is this distance is still that 2 minus x, but we're making a half of a circle. And in order to find the area of a circle, we really need the radius, which in this case is going to be half of that total distance there. All right, let's put it all together then. We know we're going to be evaluating this from 0 to 2. It's the same bounds because we're doing the same general shape here. And the area of a circle is pi r squared, but we're really only doing semicircles. So I'm going to add a 1/2 right here because we're doing half of pi times r 1/2 2 minus x squared. And before we evaluate this, I'm going to simplify this all a bit. Specifically, I am not even going to square the binomial. What I'm really just going to do is worry about that coefficient. So when I square 1/2, I get 1/4, and then I have 1/4 times 1/2, which is 1/8, and we still have that pi. So I have pi over 8 times the integral from 0 to 2 of 2 minus x squared dx, and look, we already evaluated this, right? This was A. So I'm going to jump straight to that answer, and I'm going to give a final answer of pi over 3. What if the cross sections are perpendicular to the x-axis are rectangles whose heights are 3? Well, then the area of our rectangle would be 2 minus x times 3, because every single height will be 3, or 6 minus 3x. And this is a really simple integral. We're going from 0 to 2, same bounds, of 6 minus 3x dx, which would really be 6x minus 3/2 x squared, evaluated from 0 to 2. When I plug in 2, because I don't need to worry about that 0, I do a little bit of calculating, and I get an answer of 6. Ooh, and last but not least, what about cross-sections that are perpendicular to the x-axis that are equilateral triangles? All right, let's think about this one. An equilateral triangle, we know it has 3 congruent sides and 3 congruent angles. And that means this base, we'll say, is the base of our cross-section, 2 minus x. So in order to find the area of a triangle, I need to figure out this height here. And this is where I'd asked you all to look up our 30, 60, 90 things. So let's go through. This short side is really going to be half of this full length. So I'm just going to write it as 1/2 times 2 minus x. And if I compare the short side to the long side, and this, remember, is figuring out your 30, 60, 90 triangles, I'm going to take that short side, so 1/2 times 2 minus x, and I'm going to multiply it by the square root of 3, which means the area of these triangles will be 1/2 base, which is 2 minus x, times this height, 1/2 times 2 minus x times the square root of 3. Just like with our last one, I'm going to set this up and pull out the pieces I really don't need. So the integral from 0 to 2, well, 1/2 times 1/2 times the square root of 3. I'm going to write that as square root of 3 over 4 on the outside. We have 2 minus x quantity squared dx. And you guys, that was A as well. And so I really have the square root of 3/4 times that 8/3, or a final answer of 2 square root of 3 over 3. We have one more, and we're going to do a lot of setup here, but I'm going to invite you to solve these either on your own by hand to practice your integration or using your calculator. I'm okay with either. So it says find the volume of a solid in which the base is the radius of a circle. Sorry, I wrote that wrong. Find the volume of a solid in which the base is a circle of radius 3 units whose cross sections are described. All right, so 1, 2, 3, 1, 2, 3, 3. This is not going to be a very good circle, I can already tell you that. Okay, well, forgive me. So we know that this circle is x squared plus y squared is equal to 9 because the radius is 3 and it's centered at the origin. That means we're really going to have to break this up into two different functions, a top function and a bottom function. But don't you worry, it's not that hard. We're going to solve for y and take the square root. Positive or negative square root of 9 minus x squared. So this top one is obviously the positive version. This bottom is the negative. Why did we need that? Well, we need to figure out what this cross-section length is. And we need the top function minus the bottom function. So our cross-section length, we'll say, is the top, square root of 9 minus x squared, minus the bottom, negative square root of 9 minus x squared, which would give me minus a negative, means plus a positive, 2 times the square root of 9 minus x squared. This is this length right here. We're going to use that in a lot of our pieces. First one says perpendicular to the x-axis, and they are squares. All right. Well, what are our bounds? We know that we go from -3 to +3. And if the cross sections are squares, we are taking this base, 2 times the square root of 9 minus x squared, and we are squaring that. Actually, we'll do this one. If you want to fast forward, you can. When I square this, I really get the integral from -3 to 3 of 4 times 9 minus x squared, and you can either pull that 4 out front or keep it in there. Another thing we could do, and this is maybe something just worth noting, is because this is a circle and it is perfectly symmetric, if I take the integral from 0 to 3 and I multiply it by 2, I will get everything, which is sometimes easier to evaluate an integral with 0. So let's do that. I'm going to pull the 4 out, and I'm going to multiply everything by 2. So that would be 8. 8 times the integral from 0 to 3, because we're going to be doubling this, of 9 minus x squared dx. So I really get 8 times 9x minus 1/3 x cubed, and we are evaluating this from 0 to 3. See, the 0 bound kind of drops off, and we don't need to worry about it. 9 times 3 is 27, and 3 squared is also 27. So I have 27 minus 27 divided by 3, which is 18, and then times another 8 would give me a 144. Like I said, I think we're going to set up the rest, but I will let you evaluate them in your calculators. So for this next one, cross sections perpendicular to the x-axis are semicircles. All right, so let's think about it again. The area of a circle is pi times radius squared. In this case, our radius is going to be half of this cross section. So it's actually just going to be the square root of 9 minus x squared squared. But of course, if we are doing semicircles, we only want half of that area. So 1/2, oh no, 1/2 times the integral from -3 to +3 of pi times square root of 9 minus x squared dx. Again, if you want to do it by hand, that would be really good. Otherwise, with your calculators, that works as well. I got 18 pi. What about cross sections that are equilateral triangles? Once again, I'm going to sketch out a little equilateral triangle here. All 3 sides are the same. I know that the base of my triangle is 2 times the square root of 9 minus x squared. And we need to figure out this height. So that means I technically need this, which would just be the square root of 9 minus x squared. And that makes my height the square root of 3 times the square root of 9 minus x squared. Thus, my area of our triangles would be 1/2 times the base, 2 times the square root of 9 minus x squared times the height, square root of 3 times the square root of 9 minus x squared. And I'm going to write this actually as the integral from 0 to 3, and we're going to multiply it by 2. Remember, we're just doubling because we know it's a circle and we know it's symmetric. So 2 times the integral from 0 to 3 of, well, I'm going to cancel those out, square root of 3 times 9 minus x squared. How did I get that 9 minus x squared? Well, because we're doing the square root twice. Again, if you want to pause it and evaluate it for yourself, that's really good practice. Otherwise, I got 36 times the square root of 3. All right, what about cross sections that are perpendicular to the x-axis that are isosceles triangles whose hypotenuse resides along the base? Ooh, let's think about this. Isosceles triangles whose hypotenuse is along the base. So these two sides are the same, and the base is our 2 times the square root of 9 minus x squared. And if we think about it again, we have to cut this and figure out this height. But luckily, because it is an isosceles triangle, I know that these two are the same, and this is 90. I did not do a very good job of, oh, okay, hold on. I'm very sorry. I gotta back up because I missed one really important thing. That makes a difference. Okay, it's not just an isosceles triangle, it's an isosceles right triangle. All right, let's redraw that. Which means, oh, sorry, that was terrible. This angle is a right angle. The hypotenuse, the base, 2 times the square root of 9 minus x squared. Okay, that's important because if it's a isosceles triangle, an isosceles right triangle, I know this is 45 degrees and this is 45 degrees, which is important because when I find this height, I now have another isosceles triangle. So these two sides are the same. Well, this guy down here is half of the whole base, so it's just the square root of 9 minus x squared, and that's going to be our height as well. Which means this integral will be, we'll go from -3 to 3 of the base, 2 times the square root of 9 minus x squared times the height, square root of 9 minus x squared. But I'm forgetting the 1/2 base times height for a triangle, dx. Again, try it on your own, try it in your calculator, whatever you feel. I got 36. Last but not least, what about a cross-section perpendicular to the x-axis that are isosceles right triangles with a leg residing along the base? All right, so here's, oh, that's bad too. Isosceles right triangles. Our base is 2 square root of 9 minus x squared. Well, that makes it really easy for our height. 2 times the square root of 9 minus x squared. And our integral would be -3 to 3, 1/2 base times height. So I'm actually going to write it as 2 times the square root of 9 minus x squared, that thing squared. When I evaluated, I got 72. Sorry that was kind of a low energy video. That's about all I've got to give to you guys today. I hope you have a lovely rest of your Thursday.